linked lists are marginally faster. Big O of n, the same, but from an in-depth analysis standpoint, linked lists slightly faster. So what if? What if we're at index 10 and we want to jump back to index 8? And remember, I'm not talking about an actual index, but I'm talking about what if we're at position 10 in our linked list, right? What would be equivalent to index 10? And we want to jump back 2 positions. In an array, it's easy. We just calculate the memory and go to it. But we don't have any way to go backwards in a linked list. So we have 2 options. Right? The naive way is we just iterate from the front. We just go, okay, well, we start at the head and we go okay, next, right? But this could be a big O of n procedure. So again, like we did, like we talked about, we could have a design decision where we go, hey, okay, well, our linked list, we're going to have a current pointer to point to the current node that we're at, but we're also going to have like a previous pointer, right? Or a behind, we'll call it behind, right? Behind 1 step and behind 2 steps. And so if we've got a linked list like this, right? And who knows how many are out front. And here's our current. We could have B1 and B2. Okay. And then we could just jump back to B2, set current equal to B2, and we're good. Except what's the problem there? Remember, now this is current. So we either need to reestablish where B1 is and B2 is, which defeats the whole purpose. We're right back to the big O of n procedure. Or we have to say you can't jump backwards. Or we have to start maintaining additional pointers. Now we have to maintain B3 and B4. But this list is only going to be so long before it becomes unwieldy. And the more trailers that we hold, right, the more trailing pointers that we hold, the more we're just duplicating the list. So if we're going to duplicate the list, let's duplicate the list. So let's create a doubly linked list, a concrete data structure where we've got doubly linked nodes like this. Now we've got our singly linked list going this way, but we can also go this way backwards. It's structured identically to a singly linked list, except we have our previous node just not next. So it is similar to having 2 different singly linked lists, one going each direction. And it is important to point out that the thing before the head node is going to be none, and the thing after the tail node will also be none. So we have this tail node, right? It's in the diagram. So here's the question. Do we need it? Do we absolutely need it? Or are we allowed to have a doubly linked list without a tail? And the answer is we don't need it. We typically keep it, but we need some pointer, okay? It is conventional for a doubly linked list to have a head and a tail, but there's nothing against the rules that says you only need a head, right? You're allowed to have that. Or only a tail. I've never seen anyone do that. It seems like a really bizarre way to think, but it's not verboten. You're allowed to do that. But this is the traditional conventional way. Similarly, with a singly linked list, it is absolutely acceptable to have a tail node. If you're going to be doing a bunch of adding behind the last node, it makes all the sense in the world to keep a tail node. But conventionally, you only need a head node. So remember, design decisions.